indicator random variables. Indicator random variables. So again, we're talking about not new concepts, we're still talking about expected values. It's just different tools and techniques. So, we saw linearity of a sum and how that can be useful. We saw build-up counting, okay? And now indicator random variables. Okay. So the idea here is, and the indicator random variable is a very sophisticated name. It's just another way of referring to the Bernoulli, the guy that's either 0 or 1, the binary random variable. 0 means I failed, or 1 means I succeeded. Now, you're interested in some random variable x. And the idea here is that if you can in some, sly way represent x as a sum of indicator random variables, okay, then you can compute the expected value of x using this theorem as the sum of the expected values of those indicators, those binary random variables. And the expected value of a binary random variable is easy to compute. If it's 1 with probability p, the expected value is just p. So computing the expected value of each of the indicators just amounts to computing the probability that each of those indicators is 1. And if they have different probabilities, then you have to compute a different probability for each of them. But once you have those probabilities, you just add. Okay, so let's see this technique in action. So 4 people, and I'm just going to label them by colors. So blue, okay, and they're square people. So blue, red, green, and black. They're graduating, so they all throw their hats in the air, and the hats land randomly on heads. And so you can imagine that, some assortment of hats, lands on the heads of these people, and some of them get their correct hat, and some of them do not. Okay. So, maybe the black hat miraculously lands on the black guy's head. The blue hat lands on the red guy's head. The green hat lands on the blue guy's head. Okay, and the red hat lands on the red guy's head. Okay, and so in this example, we can see that one person got their correct hat, and the other 3 got incorrect hats. And so the question we're going to ask is, when you do this experiment, when you randomly throw up the hats and the hats land randomly on people's heads, what is the expected number of people to get the right hat? Okay, now, hard exercise. So this is an experiment, and the random variable we're interested in is the number of people who get the right hat. Let's call it k. Sit down and see if you can compute the probability distribution for k, the PDF for k, this random variable. And then from the PDF, compute the expected value. That's a hard problem, okay? And you can see the text for that computation. I'm going to show you that if we're not interested in the PDF, if all we want is the expected value, we can get it very easily. So let x equals the number of people who get the right hat, and we are interested in the expected value of x, i.e. the expected number of people who get the right hat. Okay. Now you might wonder, wow, this is going to be complicated. How am I going to do this? And what's this theorem about the expected value of a sum doing here? Okay, how's that going to help us? Well, so this is where the trick comes with using indicator random variables, is to say, well, let me define an indicator random variable. So x1, okay, which indicates whether the blue guy got his correct hat. Okay, so x1 equals 1 if he got his correct hat, and 0 if he did not get his correct hat. Similarly, I can define x2, which is equal to 1 or 0, depending on whether he got the correct hat. And this guy is going to so x3 equals 0 or 1, depending on whether he got the correct hat, and x4 is either 0 or 1, depending on whether he got the correct hat. So let's see what are the values of these indicators for this example. So x1 equals 0 because he did not get the right hat. x2 equals 0 because he did not get the right hat. x3 equals 0 because he did not get the right hat. And x4 equals 1 because he got the right hat. Okay. Now, how many people got the right hat? So x, okay, is just 0 plus 0 plus 0 plus 1. The number of people that got the right hat is just 0 plus 0 plus 0 plus 1. So if you add up the indicators of whether each person got their right hat or not, if you add that up, it gives you the total number of people who got the right hat. Okay? And this is generally how we use indicator random variables. We're trying to count something, okay? And what we're trying to count is made up of a bunch of things. So we indicate whether or not each of those things occurred with an indicator random variable and add the indicator random variables. Okay? So if I want to know how many students have brown hair, I can define an indicator random variable, which is 1 if you have brown hair and 0 if you don't. I figure out the indicator random variables for each person and just add. That'll tell me the number of people with brown hair. Okay. So in general, the number of people who get the right hat, x, is equal to x1 plus x2 plus x3 plus x4. Okay. And so there we are ready to apply the theorem. The expected number of people who get the right hat, expected value of x, is the expected value of x1 plus the expected value of x2, expected value of x3, plus the expected value of x4. And now we need to compute these expectations, which amounts to computing that the probability that x1 is 1. What's the success probability for x2? Success probability for x3, success probability for x4. Okay, but now let's think about this. Everyone throws the hat, and one of them lands on blue. Okay, so and since there are 4 hats and only one of them is blue, there's a 1 in 4 chance that that the blue guy gets his right hat. So there's a 1 in 4 chance that x1 is 1. So P1, probability that x1 equals 1 is equal to 1 in 4. Okay? But if you think about it, there's no difference between the blue guy and all the other guys. Each of them gets their right hat, and the chances are 1 in 4, because they're going to get one random hat out of 4. Okay? So the probability that x2 equals 1 is also 1 in 4. Probability that x3 equals 1 is also 1 in 4. Probability that x4 equals 1 is also 1 in 4. So they're all 1 in 4. And the expected value of a binary, of an indicator, of a Bernoulli random variable is just the probability of success. So this is 1/4, 1/4, 1/4, and 1/4. And when you add up 4 1/4, well, we all knew how to do that from H2. This is 1. So the expected value of x is 1. So the expected number of people who get their correct hat back is 1. Okay, so quick exercise. What if you did this with n people and their n hats? What if there are n people? So pause the video, work it out. Same method, work it out. I'll give you 5 seconds. 1, 2, 3, 4, 5. Okay, now if you're coming back just for the ride, or if you said that the expected number of people who get their right hat back is 1, you're on the money. You know how to throw hats up in the air and compute the expected number of hats landing on heads. And now that's interesting. The ease with which we get that is just the same argument, but except that there'll be n terms here, and each of them will be 1 over n, so n times 1 over n is 1. This is an interesting conclusion. You might think that the more people there are, the more likely it is that more people on average will get their right hat. Okay, but there's a trade-off. The more people there are, yes, there are more chances to get the right hat, but each person gets their right hat with a lower probability and they exactly balance. And so only on average 1 person will get the right hat. Interesting. Okay. So let me erase, and I'm going to show you another cute application of indicators and taking the sum of indicators. Here's a quick application of indicator random variables to get a result that would otherwise not be so easy to get. Okay, so we're going to use indicator random variables and linearity of expectation. And we're going to analyze record breaking. So, record breaking. So pick your favorite sport or just your favorite thing that you're interested in. For example, daily temperatures in Troy, or the 100-meter, record, or the women's freestyle, 5,000-meter, record. Okay. So, let's imagine that, it's attempted. So there's an event where you can measure this quantity, whether it's the temperature in Troy on a given day, or the, women's 5,000-meter breaststroke race, or the men's 100-meter sprint. Okay, so you measure. Oh, it's a record. Okay, well, the first time the event happens, it has to be a record. But now you measure. Ah, it's the best, that has been seen so far. Okay, so that's a record, new record. Then, the thing happens, new record. Thing happens, new record, and so on. Okay, so every now and again, the record gets broken. And we might ask, if we go through history as a function of time, how many records are broken as there are more and more trials? Okay, how many records will be? How many times will the record be broken? So let's take an example. Okay, let's take the daily temperature in Troy. Okay, so you have, starting from, let's say, way back when temperatures were recorded, there's T1, T2, T3, T4, T5, and so on, up to Tn. Okay, so the temperatures, let's say it has happened n times. We've measured the temperature. So that's a trial. Okay, and just to simplify things, let's assume that these temperatures are all distinct. So it's never going to be the case that you have the exact same temperature on, let's say, high, the exact same high on a particular day, the exact same high. Okay, and there's no reason to believe that any one day is preferred to another. So let's assume that these temperatures are just randomly ordered. So you've got a random ordering of some temperatures. Okay. Now, on the first day, so I'll highlight the days that are record. So the first day is clearly a record, because that's the first measurement. Okay, and then maybe there's a record on another day, and then a record on another day, and so on. And so in this case, we will say that a daily high temperature, a record-breaking temperature was achieved on these red days. What that means is that it's a temperature that's larger than all previous days. Okay, and in this case, the record was broken 4 times. And we might be interested on average, what's the expected number of times the record will be broken? That looks like a very, very complicated thing to analyze. Once you break it down using indicator random variables, it just reveals its secrets. Okay, so here we go. We will define an indicator which says, was today a record or not? So x1 equals 1, because it was a record. In this case, x2 equals 0, not a record. That means it was less than T1. x3 equals 0, not a record. x4 equals 1, yes, record. x5 equals 0, not a record, and so on up to xn. So xi indicates 1 if day I is a record, and 0 if day I is not a record. Okay, interesting. Okay, so now, let's see, what's the probability that day I is a record? So what's the probability that xi equals 1? So let's think about it. You've got x1, x2, you've got the temperatures, T1, T2, T3, up to Ti. Okay? And we said that these are all distinct temperatures and they're randomly ordered. So there's one maximum, and what is the chance that that maximum is on day I? Well, the maximum, the largest of these temperatures, is equally likely to occur on any of these I days. So the chances that the maximum occurs on day I is 1 in I. Okay? So the probability that this temperature is a high is 1 over I. So that's the probability that xi, that indicates if it's a high, will be 1. So this is 1 with probability 1 over I, and 0 otherwise. Is 1 with probability, and 0, it's an indicator with probability 1 minus 1 over I. So the probability of success for this indicator random variable is 1 over I. Okay, and that's interesting. So what it's saying is that as you move further and further away from the beginning, the chances are less and less that it is a record, and that's natural. Because as you move further and further away, your temperature has to beat all the previous. In other words, the maximum must be U, which is a 1 in I chance. Okay, and so, the first day is guaranteed to be a record. Probability 1 over 1. The second day with probability 1/2 is a record, because, these two temperatures are randomly ordered, and so this guy has half the chance of being the largest, and so on. Okay, well, how many times was the record broken? It's just the sum of the xi's. So the number of times record broken is equal to x1 plus x2 plus xn. There comes the theorem with indicator random variables. So you just have to be skillful in identifying the indicator and then computing, what you want in terms of a sum of indicators. So the expected number of times record broken is equal to the expected value of x1 plus the expected value of x2 plus, that's the theorem at work, expected value of a sum of expected values plus the expected value of xn. So we just need to compute the probabilities of success for each of these indicators, but we just did that. The probability of success for each indicator xi is just 1 over I. So this is 1 over 1, which is 1, plus 1 over 2, plus 1 over 3, plus 1 over 4, plus that, plus 1 over n, which is just hn, the harmonic number. Wow, this harmonic number popping up all over the place. It's already popped up twice today. Already popped up when we did coupon collecting. Now it's popping up for record breaking. Okay? And this, for all of you who sort of, well versed in the harmonic numbers, and we had some exercises on induction to prove things about this, and even the integration method can give you, bounds for this sum. So this is approximately log of n plus a constant plus, 0.577, and this is a constant that is called the Euler-Mascheroni constant. Okay. Punchline. The number of records that you will see broken up to time step n is growing like logarithm of n, much slower than n. Okay. And so, very much slower than n. So if you take, this logarithm of n, if you take all temperatures in Troy, let's say for all of recorded history, you'll find that this is predicting about 6 or 7 times that you have the all-time high. And indeed, when you go into the almanac, you will find that it is 6 or 7 times. Remarkably accurate. Wow. Take your favorite sport, whether it's 100-meter sprints or the 5,000 meter freestyle women's, race or whatever you want, and you need to be able to compute up until today, how many trials were there, and then take the logarithm of that. Bam! You got the number of times the record breaker. Go and look and see in whatever area of interest you like, if you plot time and you see, how many times was the record broken, it'll be growing like the log of n. This is a universal phenomenon that record breaking occurs at a rate of log n when you do n trials. Wow! Isn't that impressive? Okay, so today we continue the discussion of the expected value, and in particular, we used all kinds of fancy tricks and tools to, make computing expected values easier. Indicate random variables, build up counting, but most importantly, the linearity of expectation. And so I keep telling you, memorize this poem. The expected value of a sum is the sum of the expected values. It's not really a poem. Memorize it anyway. Checking out. See you next time.